Hello and welcome to our first graduate level course on abstract algebra. By now, you may have encountered the history of modern algebra, a subject that emerged largely from attempts to solve polynomial equations. In a dramatic turn of events, the 20-year-old mathematician Évariste Galois made a monumental contribution by showing that a general quintic polynomial cannot be solved using radicals. What Galois uncovered, however, was far more than the resolution of a single problem. He revealed an entirely new kind of mathematics, one that lay hidden beneath the classical equations like a buried treasure waiting to be discovered. You may already be familiar with the story, but now it is time to present Galois' magnificent ideas in a formal and systematic way. His work is widely regarded as the gateway to modern mathematics, shaping vast areas of algebra, number theory, geometry, and beyond. The goal of this course is to help you develop a deep understanding of the core material in the abstract algebra typically covered in the first year of graduate study. This will be a rigorous and formal treatment, with undergraduate level mathematics assumed as a prerequisite. At the same time, and without compromising precision, I will make every effort to illuminate the underlying ideas and broader picture behind the theorems that we prove. Let us begin our journey. Okay, so let's look at the contents of this course. This course is actually divided into 6 segments, and we will start with groups, and then we discuss rings, then fields. Fourth segment is modules, and these are the 4 basic segments that will introduce you with the tools needed for our abstract algebra treatment. And then we discuss something called group actions. This is a preparatory, so fields and group actions, they're absolute requirement to develop our final goal, which is Galois theory. Okay. Now, notice that it is the best if you watch these in this sequence, but if you want, you can actually make some adjustment. For example, you can take group actions here, so you can watch group actions right after the groups is done. If you are in a rush to go to Galois theory, maybe you can omit modules and do that afterwards. Not recommended, but if there is a reason for you to go to the end, groups, rings, fields, group actions, these are the absolute prerequisites for the Galois theory. Okay, good. Now, let me quickly talk about the prerequisites for this one. So first of all, I assume that you have seen undergraduate level or college level set theory. And some basic results of number theory as well. And number theory is little confusing. So what I mean here is that the familiarity with unique factorization of any number into primes, Chinese remainder theorem, the totient function or Euler's theorem, and Fermat's little theorem, and you must have some familiarity with the congruence relationships, the modular arithmetic operations. Okay, so I'm not going to assume that you have to know something advanced level in congruence. For example, quadratic reciprocity and etc. Is not a prerequisite. just how to manipulate the modular operation is sufficient. And the final thing is probably linear algebra, where you have already worked with matrices, which are the linear transformation over the vector spaces. The concept of vector spaces will help um, you understand better how we can generalize that for modules when in our discussion in modules. So that's it. That's the prerequisite, and the regular undergraduate level math, maybe some basic familiarity with the real analysis and etc. So that's it. And with that, we will start with groups, and let's begin. Okay, so let's start our discussion with groups. And a quick recap what you have seen in your undergraduate course. A group is a set G along with a binary operation that is sometimes referred to as times or group multiplication and denoted using this dot. I will sometimes omit this dot and just write two group elements to denote automatically that they are operated by this binary element. And it has to satisfy the following four properties. The first one we refer to as closure. What it says is if A and B belongs to the group G, then A times B must belong to G as well. So G is closed under this binary operation. Notice that we never require that A times B is same as B times A. That is never necessary. The second condition is the so-called associative law, which says that A times and then B times C is same as A times B that times C. And notice that actually it's not that obvious, but one can prove that you can generalize it for arbitrary number of elements using induction. I'm not going to go over the proof, it's not that useful, but that's the associative law. The third one is what we refer to as the unique identity. And what it says again, that there exists a unique element that we denote as 1 belongs to the G, such that 1 times any group element G is same as G times 1 equal to G for all G belong to the group. So it doesn't matter if you left multiply or right multiply, and also there is only one unique element. If two such exist, they must be same. Okay, and the final one, that is the unique inverse. What it says is that for any G belongs to the group, there exists a unique element that I denote as G inverse, such that G times G inverse is same as G inverse times G is the identity element of the group. And this is also unique. For a given G, there is only one unique inverse that exists. Okay, so this is actually defining the group. Okay, so let's look at some examples as well as some non-examples of group. So integers, rationals, reals, they all form groups under arithmetic addition. Natural numbers, on the other hand, is not a group. And natural set of natural number, it can't form a group either under addition or under multiplication. Now these are the examples of infinite groups. We can construct finite groups as well. So for example, Z mod M is a finite group under modular addition that you have seen in the college level courses. And notice that in all these groups, all the elements, they commute with each other. So these are all the examples of Abelian groups. Now, in the next section, we will explore the non-Abelian groups in great details, and we will generate examples for them too. Okay, so moving further, just like set has a concept of subset, a set can contain another set inside. So similarly, we have something called subgroup. So we say that if H is a non-empty subset of a group G, then H is a subgroup of G. If H is a group under the binary operation of G. Binary operation of G. And we denote it like this, that H is a subgroup of G. Okay, so so first of all, in the subgroup, as you can see that essentially the elements that belong to H, they are closed among H under the binary operation. So we will see later that how knowing some subgroups of a group can tell us a lot about the group structure, the original structure of the structure of the original group. Okay, so another concept here is generator. Let's say A again is a non-empty subset of G, then the subgroup generated by A, denoted like this, is the smallest group within G, smallest subgroup of G containing A. So of course A is therefore a subgroup of G. Now we can make it little formal, and in a formal sense, all it means is that A is the intersection of all the subgroups of G that contain A as a set. Okay, but I think this language is more intuitive for us to understand how groups are generated. And oftentimes, group are generated. So oftentimes the groups are generated by a single element. So for example, if A belongs to G, then the group generated by the single element A, and we will denote it like this. We will abbreviate the notation. That is, of course, going to be a subgroup of G, is called a cyclic subgroup. And this concept is applicable in general. So, for example, any group that is generated by a single element is called a cyclic group. Okay, so the next thing that is interesting in this context is called order. Now, there are two things that we mean. One is the of an element, order of an element in the group. Um, what we mean by that is, let's say small g is an element in the group G. Then if you start collecting like g to the 0, which is the identity itself, and then g squared, and etc., at some point you must get a smallest positive integer r such that g to the r equal to the identity for some r belongs to the set of natural numbers. Now, why smallest? Because if g to the r equals to 1, then any multiple of r, if you raise that to the exponent of g, that will also be 1. But we are looking for the smallest one. So, in order to define order. So, that is the order of that element. And this must exist because the set of natural number is a ordered set. So, due to the well ordering principle. So, so this is how the order of an element is defined. Of course, notice that this order of an element is same as the order of the the cyclic group generated by G as well. Okay, so that is equal to R2. Okay, good. So this is the order of an element. Now, another thing is order of the group. This is simple. So if G is the group, then the order of the group denoted like this is defined as the number of elements in the group. Now, this entire discussion of order makes sense when the group is finite. For infinite group, R is infinity. It doesn't make a lot of value there. But the order of a group is a very important, um, I would say, property of a group. So just by looking at the order, we can actually say a lot of things. We'll get there at some point. But this is a very important thing. This will play a very important role in this course. Okay, so before we go ahead and explore the properties of cyclic group, let's clarify one thing regarding the notation. We just said that if R is the order of an element A in a cyclic group, then A to the R is identity, or 1. Now, what we had in our mind is for the elements of this group is the group looks like this: 1, a square, all the way to a to the r minus 1, which is why a to the r is same as identity. Now, this is actually the multiplicative notation that is being used for the binary operation of the group. We could have used the additive notation, and in that, the elements should look like 0, then a, and then twice of a, and all the way to r minus 1 times a, right? And in this notation, we should have said that a times r equal to 0. So throughout the course, we will mostly be using multiplicative notation. Sometimes we might use the additive notation as well, but it should be clear from the context. Okay, so just a caveat. Okay, good. So now let's explore the cyclic groups a little bit. Good. So first thing that we will do, we will state a proposition, and you have seen that in your undergraduate course. We are not going to prove it here. The proof is pretty straightforward. What it says is that if G is a cyclic group, so it is generated by A, and if we know that the order of A is n, if that is known, then how are we going to find the order of an arbitrary element? So, for example, a to the r. So, the proposition says that the order of an arbitrary element a to the r is same as n divided by the GCD of r and n. So, it's a very nice result, I would say, because it actually helps us understand the almost entire structure of a cyclic group, and you can find the order of any arbitrary element. So yeah, I mean, this is I'm not going to go after the proof here, as I mentioned, but make sure that you can do an option, take it as an optional homework. Now, using this thing, we can state something that is interesting, a little more interesting, which is going to be our second proposition, and that says that so if G is finite and cyclic, if G is finite and cyclic, and let's say the order of G equals to n, then for each divisor d of n, so every d that divides n, for each divisor d of n, there exists one and only one subgroup of G of order n divided by t. Okay, now the proof, the we will be doing a lot of formal proofs in this course, but for this one, what we are going to do, will just motivate how the proof should look like. So you can call it the proof idea. So okay, now since G is finite and cyclic, then what we can say about G is that, let's say, the set G looks like this. Let's let A be there is an identity, and let A be the generator of G. So A and then A square, and then let's take let's say the order of G is 15. So I'll go all the way to A to the 14. Okay. Now, so we know, for example, that 3 divides 15. So is there a subgroup of size? So is there a subgroup of size 15 divided by 3, which is 5? Well, yes, because I can always think of the subgroup, which is 1, a cube, a to the 6, a to the 9, a to the 12, right? So I'm just picking, it's just a visual game. I'm just picking the right element, and of course, as you can see, if you call that h, then this will imply that the order of h is equal to 5. So you know how to construct these subgroups. And if since 15 is fixed and 3 is given, of course 15 divided by 3 is unique, that will automatically guarantee that this is unique. The question is, can there exist another subgroup of order 5? Okay, now let's say there can. For example, then what is the smallest element? What is the smallest exponent? I'm sorry, what is the smallest exponent? let's take any arbitrary number. Let's say if there exists an group X or not. And of course, 1 has to be there. And let's say the smallest exponent is 4. So a to the 4, a to the 8 has to be there, a to the 12 has to be there. Now, a to the 16 means a. Well, but that's a contradiction, right? Because we said that this is the smallest exponent, but here uh, we are finding that there is always an element of a to the 1. So that means if you choose any number that is not a divisor of 15, you can just see visually that whenever it is trying to cross the order of the group, just because the remainder is always smaller than the divisor, you always get a contradiction. So that actually proves this idea. So this is a very nice result. The reason why we are not giving a formal proof of this, because we will prove a very powerful result that is applicable in general for any abelian group, not necessarily for the cyclic group. But this is just a fun game in order to develop some visualization in terms of how we should be thinking about different constraints that exist in the cyclic group. Okay, so moving a little bit further, just like we had the concept of map between two sets, we can extend that for groups as well. The additional thing that we have to take care of is the map between two group must preserve the group structure. Okay, so for group, these are called homomorphisms, homomorphism. And in order to preserve the group structure, we actually had to impose an additional constraint in the definition. So F is a homomorphism between two groups, G1 to G2, such that it preserves the structure, which formally means that for all A comma B belong to G1, it must imply that f of A times B, this times is the binary operation on G1, maps to f of A times f of B, and this times is actually the binary operation on G2. Okay, so this is actually sufficient, and one can show um, quite in a straightforward way that it automatically will imply that the identity in G1 will get mapped to identity at G2 as well. Okay, and also, for example, if X belongs to G1, then it will also imply that X inverse f of X inverse will be f of X inverse as well. Okay, so it guarantees that it preserves the group structure. Now, having said that, just like for map, we had various different maps in terms of injective and surjective, etc. We have the similar thing for group. So let's list them. So we have something called monomorphism, which is essentially injective homomorphism. And then we have epimorphism, which is surjective homomorphism. And isomorphism, this is very important, and we will discuss it in great details soon. And this is bijective homomorphism. Also, I think we can think about something called endomorphism. This is a homomorphism between group to itself and also automorphism. This is actually an isomorphism, again between a group to itself. Okay, so these will be used in various different theorems that we are going to prove. Isomorphism is especially important because there are some fundamental results that we will prove and we will be using a lot throughout this course. Okay, let me give you a quick example of isomorphism. And I'm gonna do that by reminding you some basic number theory result that you probably also saw in the college level course. Let's say that p a prime number, and also let's say a is a natural number less than p, such that that will automatically imply that the GCD of a and p has to be equal to 1, right? If a is greater than 1 and less than p. Now let's think of these elements. So a to the 0, which is of course 1, but think of these elements modulo p. A to the 0 mod p, a mod p, a squared mod p. And if you continue this way, at some point you know that a to the p minus 1 mod p, this is known as the Farmer's theorem that you may have seen. So that is exactly equal to identity again. So you are going back here. So these elements actually form a cyclic group. Cyclic group. And let me denote them by ZP, but they form a cyclic group under multiplication. So let me denote it by this ZP cross. Now also note that the order of this group is actually p minus 1. Now, the way I have constructed this group, notice that this group is actually isomorphic to our regular addition, the regular zp minus 1 under addition, our regular z modulo p minus 1, right? Because, and the isomorphism is coming from the fact that the exponent here, all these exponents, they actually get directly mapped from 0 to p minus 1. These are the natural numbers. These are exactly the elements of this cp minus 1 under addition. So this is a nice example of isomorphism, which actually leverages the nice property that is given by the Farmer's little theorem.